Current can be generated by moving a magnet in and out of a coil of wire. As the magnet enters, the magnetic field strength inside the coil increases, and induced voltage in the coil is directed one way. As the magnet leaves, the magnetic field strength diminishes, and voltage is induced in the opposite direction. Greater frequency of field change induces greater voltage. The frequency of the alternating voltage is the frequency of the changing magnetic field within the loop. It's more practical to move the coil instead of moving the magnet, by rotating the coil in a stationary magnetic field. A machine that produces electric current by rotating a coil within a stationary magnetic field is called a generator. A generator is essentially the opposite of a motor, converting mechanical energy into electrical energy. Starting perpendicular to the field, the loop has the largest number of lines inside. As it rotates, the loop encircles fewer of the field lines until it lies along the field lines, when it encloses none at all. As rotation continues, it encloses more field lines, reaching a maximum when it's made half a revolution. The magnetic field inside the loop changes in cyclic fashion. As the loop rotates, the magnitude and direction of the induced voltage and current change. One complete rotation of the loop produces one complete cycle in voltage and current. The voltage induced by the generator alternates, and the current produced is alternating current, AC. The standard AC in North America changes magnitude and direction during 60 complete cycles per second, 60 Hz. The generators used in power plants are much more complex than the model discussed here. Huge coils made up of many loops of wire wrapped in an iron core to make an armature much like the armature of a motor. They rotate in the very strong magnetic fields of powerful electromagnets. The armature is connected externally to an assembly of paddle wheels called a turbine. While wind or falling water can be used to produce rotation of the turbine, most commercial generators are driven by moving steam. At the present time, a fossil fuel or nuclear fuel is used as the energy source for the steam. You need an energy source of some kind to operate a generator. Some fraction of energy from the source is converted to mechanical energy to drive the turbine. The generator converts most of this to electrical energy. An electric current in a coil is deflected in a magnetic field, which underlies the operation of the motor. Electromagnetic induction underlies the operation of a generator. We'll call the deflected wire the motor effect, and the law of induction the generator effect. When a current moves to the right, there's a force on the electrons and the wire is tugged upward. When a wire with no current is moved downward, the electrons in the wire experience a force creating current. The motor effect occurs when a current moves through a magnetic field. The magnetic field creates a perpendicular upward force on the electrons. Because the electrons can't leave the entire wire is tugged along with the electrons. In the generator effect, a wire with no current is moved downward through a magnetic field. The electrons in this wire experience a force perpendicular to their motion, which is along the wire. A current begins to flow. A striking example of a device functioning as both motor and generator is found in hybrid automobiles. When extra power for accelerating or hill climbing is needed, this device draws current from a battery and acts as a motor. Braking or rolling downhill causes the wheels to exert a torque on the device, so it acts as a generator and recharges the battery. The electrical part of the hybrid engine is both a motor and a generator.